This is example 10-9, pump in a pipe loop. So you can see here we have this branch, two branches of a loop. The water comes in at C and exits at D. We're given the velocity of the flow coming in and the diameter, so we know what the flow rate is. We know what the flow rate is at C, we know it at D. So what we're now trying to figure out is how much the pump how much energy the pump has to add so that the flow is equal between the two branches. It's not clear from this picture right here, but the branch going from C to A to D is twice as long as from C to B to D, right? But if we want to start out, we can say that if the diameter is the same everywhere, right, then we can say that QC is equal to QD, which is then, of course, just call it Q, I guess, is VC times AC is equal to VC times pi over 4 times D. Well, we don't have to really say DC because it's the same everywhere. So it's called D. Now we also know that QA and QB are supposed to be the same, right? Equal flow. So we can say QA is equal to QB, and if they're supposed to be the same, then of course they'll just be the half of our QC, right? So we can say that would be Q over 2. So if we divide our term here by 2, then we can say that be pi times VC times D squared divided by 8. All right. So now we have our velocity in the pipes here. How about the velocity at A, right? We'll need that to figure out what our head losses, what our major head losses are. So we can say VA is then going to be QA divided by AA. QA we said was pi times VC times D squared divided by 8. All that divided by pi over 4 times D squared, which means we can cancel out a whole bunch of stuff and we'll get VC over 2, which makes sense, right? If the diameter is the same everywhere and the flow is half through A, half through B, then the velocity should be half in those pipes if the diameter stays the same. So that would be, where do we have it? 3 meters per second here in the picture. 3 meters per second divided by 2 is equal to 1.5 meters per second. So that would be our velocity. Now that we have our velocity, we can calculate our Reynolds numbers to see if we're laminar or turbulent. So REB is equal to REC is equal to rho times VB times D. We can do VB or VC, doesn't matter, it's the same, divided by mu. Then we have to look up what our density and our viscosity are at 20 degrees C. We can do that in the appendix. So we'll find that this is 998.3 kilograms per cubic meters times 1.5 meters per second, which is calculated. Our diameter of the pipe is 0.75 meters, right, 75 millimeters. And we divide that by the viscosity, 1 times 10 to the minus 3 Newton second per meter squared. That gives us a Reynolds number of 1.12 times 10 to the 5, which means we're definitely in turbulent territory. So we'll have to see what our roughness is. Our roughness is galvanized iron pipes. So we'll have to look that up. Galvanized iron pipe. Well, we can look that up on our figure of the Moody diagram. So we can say that's right here. So that would be epsilon equal to 0.15 millimeters. That means epsilon over d is going to be 0.15 millimeters divided by 75 millimeters equal to 0.002. All right. With that, we can go into our Moody diagram. So this would be our RE of 1.12 times 10 to the 5, right there. And then we are looking at 0.00202. 202. That's our green line right there. So we see where it intersects. Be 0.0255. 0.255. All right, so we can say from the Moody diagram, from Moody diagram, F is equal to 0. Oops, I forgot a 0 in my picture up there. 5. So erase that and write that correctly here. 0.0255. There we go. That means we can go ahead and plug everything into our Darcy-Weisbach equation. So we can say HLB, for instance, would be F times LB over D. Right? F doesn't matter if it's B or C because it's same velocity, same pipe and everything. Times VB squared over 2G. Plug that in, we get 0.0255 times the length in the longer direction where our pipe was 120 meters. Long pipe. 120 meters divided by the diameter, which was 75 millimeters, times VB was 1.5 meters per second, squared divided by 2 times 9.81 meters per second squared. And that gives us a head loss of 4.67889 meters. So that's the head loss in my pipe that goes the long way around. You can do the same way for the short way around, right? That would be HLC is equal to F times LC over D times VC squared over 2G equal to 0.0255 now times 60 meters, 0.075 meters times 1.5 meters per second squared, 2 times 9.81 meters per second squared. And that gives us, to no surprise, exactly half of the other one. 2, 3, 3, 9, 4, 5. Right? Has to be exactly half because the only difference was the length. Now, if we go back to our picture, right, we have parallel pipe branches, then we know that the head loss or the energy loss along both these pipes has to be the same. That means if the energy loss is supposed to be the same, then the difference between the two has to be supplied by this pump, right? So we can say that H pump, right, will just have to be HLB minus HLC, and that is 4.67889 meters minus 0.2349. Nope, that's not what it was. 3945 meters, or 2 point. Got this wrong here. That's not 0 point. Why do I have 0 point up there? Wrote it wrong even up here. Let's see, 2.33. Let's get rid of that one too. 2.33945. Now I have it right. 2.33945 meters. Now that is 2.33945 meters. Right, again, makes sense because one was half of the other. Last step we have to do then, we have to find the power of the pump. So W pump is then equal to rho times G times Q, now B, right, has to be the flow there, times H pump is then equal to, well, we don't know, we never calculated what that flow was, so we can say that would be rho times G times pi, oh, we did calculate above, right? So pi times VC times D squared over 8 times H pump, and that is then 998.3 kilograms per cubic meters times 9.81 meters per second squared times pi, let's go a little closer here, pi times VC was 3 meters per second times VC. Right here. Yep, VC is 3 meters per second times our diameter, 0.075 meters squared, divided by 8, and then times pump the pump, 2.33945 meters. And that gives me, I had a calculation error before, so let me recalculate that real quickly. 998.3 times 98.1 times pi times 3 times 0.7 squared divided by 8 times 233,945 gives me 151.8264 watts, or 152 watts if I round to 3 significant digits. All right, so with that, we have now found that if everything's the same, right, if both flows are supposed to be the same through the 2 branches, then we'll need a pump with 152 watts to make sure that the flow stays the same. Otherwise, the flow through A would be higher than through B.